Notice how this microwave oven hums a little bit louder when it starts. And I figured this is due to transformers when they start. Sometimes they have quite a surge in current if they're started at right at zero crossing during the cycle. But I was wrong. This piece of wire has got a 0.1 ohm resistance, so I'm using that to probe the current on my very unsafe wiring. So let's probe the startup current. Yellow trace is voltage, blue trace is current at 1 ampere per division. And you can see it spikes quite a bit initially, but then it settles down within a few cycles. So that would not be accounting for this hum that we hear at the start. And that spike here is in fact because the transformer started at a slightly unfortunate phase in the voltage, and so its magnetic field got out of balance. The induced voltage in a transformer is a function of the rate of change of the flux, but if you're controlling the voltage, then the flux ends up being essentially the integral of the voltage, and when the voltage is at the zero crossings, the flux is always at its maximum. But if we turn the transformer on right when the voltage is at a zero crossing, it will start out with zero flux, and then as we integrate over this part of the curve, our flux goes way up. Problem is, the core is usually run very close to saturation just because that makes it for a smaller transformer. So we're already starting to run into saturation right about here. And if we look at a typical BH curve for a typical magnetic core material, on the vertical axis we have the flux density, and on the horizontal is how much magnetizing force, which essentially comes from current, there is. So as you can see, as we get closer to saturation, we need a lot more force. And so as we get to peaks of flux density, we get these little bumps in current because we're already close to saturation. And if we're trying to go way past saturation, it just won't go any further, and the flux density will not increase, which means we don't take up that voltage with induction, which means we have a lot of excess voltage, which turns into a lot of excess current. And that's what happened here. We get this huge spike in current because we're trying to drive more flux into the core than it can take. And since it's not taking any more flux through it, we have less inducted voltage taken away, which means all of it is through resistance. But as a result of this, it balances itself fairly quickly. So you can see the current spikes a little bit higher here and here, but then after about 2 cycles, it's actually balanced itself. But I don't think that was even worst case. Let's try it a few more times. I'll just set the scale to something smaller so we don't saturate, and run that a few more times. So this time we started probably at the top of a cycle or close to it, so we don't get that much spike. Again. That one is a bigger one, although we actually had a bit of the other half of the cycle here too, so let's try a few more times. There, it seems to be pretty one-sided. So the current is about 3 times what the peak current is under normal operation. I think that's about as high as I'm going to get them. Now this only lasts maybe 2 or 3 cycles, but the hum when the microwave starts up is 1 second to 2 seconds. So obviously this is something else. So let's look at a longer trace. At half a second per division, we can see that after 3 divisions here, the shape of the current waveform changed quite a lot. So initially we have this rather funny, bumpy looking waveform for the current, which is not very much in phase with the voltage. And then a bit later, the current waveform increases and is also in phase with the voltage, or in this case 180 degrees out of phase. It's just a matter of polarity. So this is when the microwave is actually starting to make microwaves and consume power, and I'm assuming that that is suppressing the magnetic field in the transformer a little bit because now it's loaded. So essentially the secondary winding is working against the primary winding in the transformer, causing less magnetic field and therefore less hum in the transformer. So that suggests about 1.5 seconds between the microwave starting and it making microwaves. So I want to see the microwave, so I'm just going to put a couple of broken light bulbs in here. And now with the scope and the light bulbs, and we can see that waveform change to this thing just at the same time that the light bulbs turned on. So that change in hum at the startup is the time that it takes for the magnetron tube in the microwave to actually start making microwaves. Before that, it doesn't consume a whole lot of power. And the reason there's a delay there is the filament of the magnetron tube that actually emits the electrons needs to get hot first. So basically, the tube just needs to warm up. Now, if I start and stop that microwave in rapid succession, that tube will still be kind of warm, so it should come up much faster. So if it was just microwaving, that tube is still hot and it comes on right away. But if it's been off, say, for 10 seconds, by that time it's already kind of cold. And that's caused me a lot of frustration in the past because I warm something up and it's like, oh, it only needs 2 more seconds, so I'll give it 2 seconds, and that does nothing because the 2 seconds is what it takes for the filament to get warm again, because I'm not so quick to restart it within a second or so, because first I got to check that it was not hot enough. Put it back in, give it 2 seconds, does nothing. But I really wanted to talk about transformers and magnetic fields, so let's get back to that. So this is the current waveform in blue of the microwave before it's actually making microwaves, and notice how it bumps up here and bumps down here right about at the zero crossings of the voltage, because that is where the magnetic field is at its maximum. Now, microwave oven transformers are actually kind of weird, so let's try a different type of transformer, a variac. Notice how safe I am unplugging it before I change the wiring. Oh shit. I forgot about that glass of water in the microwave. And clamp that wire down for safety. So I don't know if you could hear that brum at the start, but I caught it sort of at the worst time here in terms of when I turned it on. Took a few tries. And we see a huge spike in current here. We're just saturating on the scope because I managed to turn it on right at about the worst time. Right about here, I think, from all the little spikes here. And then we get this spike in current, and then we still get a little bit of spike at the zero crossings because it's not quite balanced yet in terms of magnetic field. And that actually goes on for quite a few cycles, more cycles than I captured in this trace. Let's try capturing something a bit longer. And on this one, again, I managed to get a fairly large spike in the current at startup. And those little bumps here, they last for quite a while. Still appreciably there after quite a few waveforms. And we got 1, 2, 3, 4, 5.5 divisions where this is going on, and that's 100 milliseconds per division. So that's half a second at least of that initial vrum that we could hear. So I bumped up the current scale way up, and you can see this lasts for quite a long time. This is half a second per division. Now this time, just based on the phase of when I turn it on, the current spikes are actually downwards. And then they gradually get smaller. Oh, still there. They take a long time to settle out. So now just in real time, turning it on, and you can see the spikes, and they take quite a while to settle before that waveform is symmetrical. So that initial transformer brum can take a few seconds, so it seemed plausible that that's what I was hearing in a microwave, but it wasn't. And now let's measure the current off of a just plain old transformer. But I'm running it through the variac first, which allows me to boost the voltage to up to 140 volts. And if I look at the waveform here, just by increasing the voltage a little bit, you can see the current waveform gets more bumpy as we're getting closer to saturation of the core. But let's play a little trick on this transformer. I'm going to use these rare earth magnets to throw it a little bit out of balance. I'm taping it on here just so I can get it off again later, because it really gets stuck to that transformer. And these nuts will provide a return path for the flux. And now watch what happens to this current waveform as I put this magnet on the transformer. Notice how it's also getting louder. And now we have quite a bump on one side here, not so much on the other side. And if I were to reverse these magnets or just stick this on the other side of the transformer, being careful not to short my clip leads, now the sharper spike is on the bottom. So what this magnet does is it puts some flux into the transformer core to begin with, and with there already being some essentially constant flux in the transformer, we can only add so much more flux before it saturates, which is why we're seeing spikes on here on the current. Now imagine instead of a permanent magnet here, I had an electromagnet to apply this bit of flux here, and the transformer was optimized to saturate, and the shape was also more optimized so that the electromagnet could really saturate part of this core. Then using potentially a small amount of current, if the electromagnet has a lot of turns on it, I could cause a larger current to flow through the core of the transformer. And before the invention of the transistor, some of this was actually done, called a magnetic amplifier. The Germans had perfected the magnetic material for this and actually used it as part of the controls for the V-2 rockets. And after World War II, the Americans got their hands on this technology and actually used it for some things for quite a bit until transistors became small enough and cheap enough. So interesting bit of history there.